Okay, thank you for coming today. Our talk is on hardware-tolerant hardware that's tolerant on Trojans, and we're going to talk a little bit more on that and supply chain security in practice. So the highlights of this talk is we start first discussing the private life of keys. There are also some weak links on the supply chain. We're going to bring this up. And then we have some lessons learned from airplanes. And then we'll see how we can transfer this to crypto hardware, where Dan is going to do our demo and describe the architecture we came up with. And then I'll describe the protocols, some maths, and some magic stuff we do. And finally, we'll close the presentation with some talk about politics and how we can exploit this to crypto hardware. To begin with, let's just think that we have a private key and a public key pair. How do we generate that? So first, someone somewhere in a development design house designs an integrated circuit, which is then fabricated to a foundry somewhere else probably. And then this integrated circuit is delivered to the hardware vendor that actually ordered it. The vendor then loads its firmware on it and assembles the actual device that's going to use it, the integrated circuit. And then the device is sent to the customer that bought it. The customer uses the device to generate and store the key on it. The problem with this, the life cycle of keys, is that in practice, if any of these steps gets compromised or an attack happens on them, the final key is weak or compromised completely. And this is, for this reason, we have hardware security modules. So hardware security modules were built with a purpose of protecting keys and performing all the operations on the device. So they provide some very neat features. Some of them are cryptographic key generation, storage, and management. And all those things happen on the device. And then they have a whole set of features that have to do with tamper-proof, tamper resistance, and tamper response. So what they do is basically, if you physically manipulate an HSM, then this is going to be visible to the owner of it. Also, the manipulating physically an HSM to retrieve the secrets that are stored inside is not trivial, so they provide tamper resistance. And then tamper response means that the actual HSM, the HSM can take action if it detects that it's being manipulated, so it may erase the keys or lock down completely. So this makes it very hard for the adversary to retrieve what's in there. Plus, for companies that want to check all the boxes, the HSMs are usually certified with a very high level of security and validated for it. The bottom line for HSMs is that all the operations are being carried out on the device, so the secret keys and all the secrets stored inside never have to leave the device. And for this reason, because they provide very high security, they're used in lots of applications where high assurance is needed. So like public key infrastructures, SSL connection accelerators, payment systems, it's very popular. And actually vendors are willing to pay the very high cost that comes with them. 10K that we have here on the slide is the very, very low end of it. Usually it's much higher. And then there are lots of other costs that usually are hard to quantify, but they're quite high, that have to do with integrating the actual HSM once you buy it and then operating it and supporting throughout the years. Despite the high cost, HSMs protect only the last two steps on the private key lifecycle. So the top four are still exposed. And there have been cases where we've seen things going wrong on the first four steps, meaning that the actual security of the device is being completely broken and non-existent. For this reason, and because people know that, they try to come up with solutions, and there's lots of academic literature on it, actually. The most popular of those are trusted foundries, so this means that you send your circuit design to a foundry or factory that you completely trust, not to insert any Trojans in it. The problem with it is that it's very expensive, and of course, mistakes can still happen during fabrication. The other approach is more academic. It's split manufacturing. There should be few foundries that support that. It's still expensive, and again, errors may happen. And the final one is post-fabrication inspection. So what happens is that you order your integrated circuit, they manufacture it, you get it back, and then you run some tests on it. The problem with this is that it's expensive. You need expensive tools to do that. You need to constantly retool because techniques advance. And then it's a huge pain because if you order like a few thousand chips, you cannot test all of them. So it doesn't scale very well. In general, overall, it's an arms race because hardware Trojan techniques are constantly advancing, and adversaries are always and will be always a step forward. So you can never be 100% sure that nothing went wrong throughout the process. Even your trusted foundry may sometime betray you and cooperate with someone. So on another note, there is another community, the fault-tolerant community, so not security, that they had a similar problem and they solved it using redundant systems. So what they do is basically, instead of using one integrated circuit, they use three, coming from completely different supply chains, and they build either dual redundancy systems, which allows them to detect if one of those two circuits is misbehaving and detect errors on the final results, or triple redundancy systems where all the computations are being replicated between the three different processors, and in the end they perform a majority vote about what the correct output is. And this is actually used in autopilots on commercial aircrafts, and I think also they use it in space. The problem with fault-tolerant systems is that they are built for safety and they do their job very well for that, but because they replicate the computations, but for security they don't transfer well at all. Actually, they're bad for security because what you end up having is a system that has three processors storing your secret key, meaning that if one of your processors is compromised, then you're prone to attacks. So instead of actually improving your security, you increase your attack surface. For this reason, we came up with the solution we're going to present today, which provides protection also on the four first steps of this life cycle of keys. I am Vasilis. I did this work with George Danezis, Dan Svercek, and Pertus Venta. And here are the ingredients of our solution. So we have two ingredients. One of them is hardware components, and the second is cryptographic protocols. And we need specific things from from these components. So for ICs, we need independent fabrication. So they must be fabricated in different facilities, and the supply chain leading to them, their supply chains should be non-overlapping. They must be programmable, hopefully affordable, and if they are commercial off the shelf, that's actually even better. For cryptographic protocols, we want protocols that all the parties that participate in them are not trusted, that the secrets are completely distributed and allow them to perform operations in a distributed manner instead of a centralized one. And they are provably secure, meaning that there are maths that support their security. So, our hardware components are smart cards. Because you have many independent manufacturers who have their own facilities to produce smart cards, and the supply chains are indeed disjoint, both in terms of locations, design, and foundries. They are programmable and they certify to very high standards, and they are commercial off the shelf and pretty cheap actually. And then for the protocols, we have multi-party computation protocols, which allows you to do distributed operations, meaning that the key is not on a single point at any time, and you can generate random numbers in a distributed manner, do keeper generation, which is what we're interested in, decryption and signing, which is what we are also interested in. The two nice properties of those protocols are that they allow you to be secure in cases where all but one of your components are malicious and they cooperate with each other, or they allow you to be secure in cases where all your components are malicious but they don't cooperate. So now Dan is going to take over and he's going to introduce our prototype and then move on with our actual demos.
All right, thank you. So with the help of Jack, I will try to show you some live demo and what was so far pretty much slideware. I'll try to turn it into real product. And the real product look about this. And we got one prototype or one piece here on the table. And I will try to use it to show how the multi-party computation security that we designed actually works. So what's inside the box? We got many smart cards. This particular one's got 120 of them. And we will use them in groups of 3 to basically show some kind of scalability and properties of protocols that we designed. Probably you say, well, smart cards is pretty slow, cheap device. Well, we can talk to them directly at about over 1 megabit per second. So in that box, basically, we are talking more than 120 megabits per second to smart cards. So I don't think 120 megabits is really that slow, even today. There is some FPGA to connect all the pins together, and those boards are connected with standard Ethernet through some internal hub into main internal motherboard, and then just put it to a rack and use it in scale. So here's just the main parts. So 120 smart cards. We use Java cards because they are easy to program, and we did some development for Java cards, so we can use really very easily Java cards from different manufacturers. Something we presented earlier at Black Hat. So each smart card gives you physical security, very good, several layers of physical security that makes it very, very difficult to get inside and extract any keys. Among other things, all the memory and addressing in the smart card is encrypted, so just deleting one AES key basically destroys all the information and makes it basically random data. We got FPGA that basically connects Java cards, and we use serial protocol to talk to Java cards into basically TCP packets. And then you got internal network hub and main Linux server that runs for us basically untrusted RESTful server that allows connectivity to outside. So we got 3 demonstrations. So I will try the first one, which is about showing geographically distributed control of integrated circuits. What I will use is my laptop. I will use a black box that is next to me. There's got 120 smart cards inside and runs the RESTful server I will talk to. But I will also try to connect to another set of 120 smart cards that are just now sitting in our Cambridge office in the UK. So if everything goes well. So I will load one of the dashboards. So at the moment it's all green, all red, because we don't have any data here yet. Let's start the glue that connects the RESTful server to the visualization dashboard. And now let's switch the font. Now you can see that what I actually did is I started the server with configuration that shows 2 IP addresses that hide 2 sets of smart cards. One is local address in the server, the other one goes all the way to the UK through some commercial ISP. This is an enumeration of the smart cards, and what's happening now is basically the RESTful server should be starting any second. So what is happening, basically the server will try to connect to all those smart cards. It takes longer than elsewhere. Still not started. Yeah, here you go. So it took a while, but at the end we got there. So now we got basically available 240 processors that are each able to basically run multi-party computation for us. So the nice thing about the system as we designed it is that not only you can use microcontrollers different geographical locations, but each multi-party computation, each group can contain processors that are in different physical locations. So you can run a group that's got one processor in here in the room, another processor in Cambridge, another one actually can be run as Java card simulator, and as such on any platform as it ARM, Intel, on Spark. So it gives you really wide range of options to provide different supply chains and complete independent manufacturing processes. So basically the only common point when you start using crypto generate keys is your laptop when you actually start to generate a key. So I'll quickly switch point off. So it should be much, much quicker. Now I got basically just local address for the board in here. We'll change different backboard for throughput. So got something there already. And what I'm going to do now is use my laptop as a load generator and start running requests against the smart cards. So what I'm going to do is basically create 30 independent groups of smart cards with 30 different keys that can basically serve 30 different customers at the same time. So instances have been allocated, and now basically this is transactions per second. We run for about a minute. If I just sort of a bit of context, imagine that you use bitchain or blockchain technology and you got 5, 10 parties in a private scheme, and basically each transaction needs 10 signatures by 10 parties. What you can do with this computation is basically involve all those 10 parties, but as a result you got just one signature, but you know that the signature needed cooperation of all of them. So it's much easier to verify signatures because instead of going to 10 different ledgers, you got just one master copy that you can replicate and verify independently. Right, so this basically just demonstration of the throughput of the whole system and the scalability, and Vasilis will show a bit more graphs about our previous tests that we did. So the last demo is actually showing how someone can try to attack the whole system, but he needs to put a lot of effort into it to actually succeed. So again, just one server that is running here, laptop connecting to it, and I will have a small group of smart cards that got backdoor inside. And the attacker will try to use the RESTful server, the thing that is facing the internet, and will try to set the key that I will use to some kind of default value so we can easily decrypt the data. So again, I'll turn the dashboard to something new. So I'm using dashboard and also Node-RED to basically connect all the flows and show you something meaningful. Oh, it's bigger than I thought. Anyway, there are two main flows. One is to generate key. I don't know how well it is visible. So this is to generate the key, and then I got 3 triggers that will allow me to compromise card 1, 2, or 3. How it happens is each time I'll need to create a RESTful request that will open the backdoor that was imparted in the chip, and then basically I will try to generate key and see if the key is of the value that I assume, that I expect, so I can attack the whole system. So the first one will be, so let's initialize the dashboard, so we got in sort of initial state. So now there are 3 cards used, because we did some experiments before. All is green, but you see that there is no key, and there is no group that we can use. So let's run create. As a result, I got now 3 addressees, so identifiers for integrated circuits that I will use. Now it requires a little bit of clicking. What I'm going to do is basically do what the attacker would do. Figure out which are the processors that he wants to compromise. So this is the first one done. So this is the second one. And the last one. Almost there, bear with me. So last bit I need is to tell the key generator algorithm which group of cards it should be using. So confer deploy. Make sure that we've got all cards as they are. They are secure. Now we try to generate new key. We got some delays here, so you can actually switch quickly. So you see that there is now a public key, and it's definitely different than the fixed key that we know the attacker set and wants the chips to share. So the first step is to compromise card 1. So we inject the backdoor to active, so the card is compromised. Takes a few seconds, and now basically the new cards, new configuration will generate new key that has changed. But you can see that it's still green, it's still secure. Imagine that basically to get this, the attacker either have to change the firmware that can be verified by us or controlled by different parties, or have to compromise manufacturing of the chips anywhere during the manufacturing process. So if I do card 2, so compromised. Now imagine that all those keys are elliptic curve to 256-bit keys, and if at least one part is secure, we still got 256 bits of random data, random key. So second attempt still didn't succeed. I'll try finally the third card. Now I basically assume that the attacker compromised 3 different places, 3 different chips that can be under control of 3 different parties, manufactured or running on different hardware from 3 different manufacturers. And only then, when he does all 3 of them, you can see that the key is as expected, and now we can basically decrypt all the data that we try to encrypt with a key or forge our signature. On the other hand, if I expect that this can happen and regularly try to refresh the chips that I use, if I refresh just one of them and turn it into secure state, then I again get key that is absolutely secure from a cryptographic point of view. All right, so that was a bit of live demo, and Vasilis will tell you what it's actually doing inside.
Okay, thank you again. So yes, we've built that system. However, for our demos, we used a group of cards that had 3 cards inside to do all the computations. However, someone, for whatever reason, he may want to use less or more cards, so we try to optimize our protocols to be scalable. So for signing a decryption, we do super well. This means that you can use as many cards as you want, and the processing time doesn't increase, and the processing time per operation. For key generation, because we need very high assurance, this is not the case, but as you can see, it increases linearly, so it's nicely. It's not that you get a devastating delay. For scalability, on our hardware here, we used 120 or 240 if you use hardware remotely. You can add as many processors as you want. As you can see, both operations, decryption and signing, the throughput increases linearly, so the more you add, the faster you become. So depending on your need, you can decide how many processors you want to use. So a little bit more about the magic that's going on behind the scenes. I kept it extremely light in terms of mathematics, so there is nothing there. so there are 3+1 key points that we wanted for each of the algorithms we used. So the first one is that there must be no single processor handling sensitive stuff such as secret keys or anything else at any time. The second one is that if one of the processors is misbehaving and is trying to actively attack other processors or trick them into doing stuff, honest processors can detect that. The third one is that if one of the honest processors is being excluded from the protocol execution, the user can actually tell that this happened. And finally, if we could come up with a protocol or an algorithm that is doing well in terms of performance, which we did. So a little bit of a side note, secret sharing is a very neat concept. So imagine you have 3 people and they want to share a treasure map. The simple solution would be so that they can retrieve the treasure only if all of them get together again. Otherwise, no one can actually retrieve the treasure map. So the naive solution would be to actually cut the treasure map in 3 pieces, and then each one of them gets one of the pieces. However, there is a problem with this because each piece is leaking a part of the information of where the treasure is, and someone may be able to successfully use this information to retrieve the treasure by himself. So there are some schemes called secret sharing schemes that they allow you to split a secret into shares, and then they allow you to recombine those shares to retrieve the original secret, to reconstruct it. But they have this very neat property that allows that each share doesn't leak any information about the actual secret. So as long as not all shares are present, you learn nothing about the actual secret that they are hiding. And then there are 2 parameters that the user can actually choose to tweak. One is how many shares you split the secret into, and the second one is how many of those shares you need to reconstruct the original secret. So you may actually cut the treasure map into 100 shares, and then you need only 3 of them to reconstruct the original map. But in this case, for our hardware, we use a 3 out of 3 scheme. So this means that we split our secrets into 3, and then you need 3 processors to come together to reconstruct them. Okay, so here are the operations. Classic key generation, you go to the HSM, you inquire a new private key for your serve. If the HSM responds, he generates a key internally, stores the private key inside, returns to you the public key. The problem is that if the HSM has a malicious processor, this means that the processor gains full access to the private key, and then the public key that you are getting back, you have no idea if this is some sort of a weak public key or there is any other problem with that. Instead, what we do is something different. So we have 3 processors, as you can see at the bottom of this slide. So on the step 1, you inquire them to generate a public-private key pair. So they generate the public keys, and then through a process they combine them to form the common public key that you can see on step 4. So what's interesting about the common public key is that despite the fact that all the keys except one may be compromised, as long as there is one key that's strong, the final key maintains its security. So going back to the key points that we evaluate our algorithms with, we have all of them except the one that accounts for performance, and this is because on step 3 there is some interaction between the processors, so this means that there is some slowness there. We've seen it previously on the graph where we showed how it scales. So then we have decryption, pretty similar process. You go to the HSM, you say I want to decrypt this email, HSM knows your key, so it decrypts the email for you, returns to you the plain text. Again, the same problem, the HSM needs to have in a single place your full key. Instead, we do something else. We do distributed decryption. So in step 1, you inquire from the HSM to decrypt your ciphertext. What happens is on the second step, the different processors generate what we call decryption shares. So the decryption shares hold no information about the plain text. They are just shares that then they send to Bob, and Bob can then combine them by himself to retrieve the plain text. So there is an added benefit for that, because the HSM never sees the actual plain text. All the decryption process happens actually by the user himself. Again, we have all the key points checked, except there is misbehaving a processor one, because there is no interaction between the processors in this protocol. It makes no sense. I mean, if you misbehave, then the plain text in the end will make no sense, and essentially the Trojan the hardware or the Trojan hardware will reveal its existence, and the user will know that something is going wrong with his hardware. Then we have classic signing. Same process, you supply plain text and you say I want to sign the plain text. The IC again needs full access to your private key, and then it returns you the signature for the document you provided. Instead, what we do is a bit different. So there is a first step, or step 0, which is caching. So when you set up the device, you do some caching. You do this once for thousands of signatures, so it takes about a few minutes, and you do this only once in the lifetime of the user. And then you move on with the actual protocol. So this is what you execute when you want to sign a document. What you do is you send your document to the HSM, they generate the signature shares, which are then on step 3 returned to the user, and the user combines them to retrieve the signature for the document. Again, we're very efficient, and at no point no one learns the full private key of the user. However, so far we've discussed cases where you have only 3 processors interacting, but our hardware uses many more. So we had the problem of how to make that thing scale. And by scaling is basically adding more groups of cards. So we ended up adding 40 groups of cards, and then we had this problem with a key that, yes, each group of cards can generate its own public-private key pair. The problem is that how we can make that key be consistent with what's the public key of Bob. So can all those groups serve requests coming from Bob? And we have to come up with another protocol that does that. And this is what we call key replication. So the naive way to do that is you have, let's say, group A and group B. Group A has the key for Bob, and then the processors inside the group share the key shares with the processors inside the group B on a one-to-one basis. So this looks fine. However, what happens is that if processors A1, B2, and A3, which we can see here as malicious, collude or cooperate, then they can retrieve the actual secret. So this is very bad, and we don't want this to happen. So this is not clearly this is not the right way to do key replication. What you do instead is you split. Each of the processors is splitting its secret to 3 secrets, and it distributes them to the processors of group B, and then this is how you do that in a secure way. I'm not going into details, it's pretty easy from a mathematical perspective, but we don't need to know that. What's important is that by the end of the protocol, both groups A and B, or whichever other groups you may have, we have 40 here, you can have more, can serve requests for the same public key that belongs to Bob or whoever else. So now the politics part of the talk. So initially, so far we've been saying that our system provides security as long as there is at least one processor in the system. So you can have many malicious ones, but if there is at least one honest, then you're okay. However, this is not always the case, or you cannot always be sure that not all your components are backdoored. And to be accurate, the adversaries that are capable of introducing hardware backdoors or Trojan horses are mainly governments. And because they have access to deep access to fabrication facilities, they use very sophisticated techniques, and they're Trojans, and the techniques are very hard to detect. And if you detect, usually you're not sure if it's an error or a bug or a manufacturing mistake or an actually malicious act. However, they're very secretive, and all those things are highly classified, and there is no chance that they will share the details of their backdoors with anyone. And we were thinking if we could exploit this somehow. So what this entails is that they are unlikely to collude or cooperate with any adversary, any other adversary. So if you remember, the MPC protocols, multi-party computation protocols, provide security guarantees against another class of adversaries. Adversaries that are all malicious, but they don't cooperate. So in this case, what you can do is basically you can buy a processor from the US, another one from China, and another one from Russia, that they are fabricated there. And then even if all of them are backdoored, you can be certain that they will never cooperate and they will never reveal their backdoors one to the other. So you're safe and secure despite your hardware being super compromised. So concluding this talk, Yes, we introduced a hardware that can tolerate faulty and malicious hardware. We have decent performance and we scale nicely, so you can move this, you can serve as many requests as you need. We use off-the-shelf components, and this is neat. I'll show you a little bit later how this is very nice. And all the techniques that we've discussed about trusted foundries, split manufacturing, and these kind of things, you can, of course, source components that manufacture securely to increase the security of the system. We're not competing with them. We can actually use them. So what's interesting is that, yes, we took it to an extreme. We built a hardware, but what you can do is you can build your own hardware-tolerant device. It's pretty easy. You can buy a USB hub and a few card readers, depending on how many processors you want to have. You can download our MPC applet, buy some cards from different countries, do your research there, where they're coming from, which manufacturer has its own fabrication facility and where this is located. Some of them are actually providing details, or you have to pay a little bit more and then they are produced in specific fabrication facilities. So download our applet afterwards, review the code, please do that, and then yes, you upload our applet in the cards, and you have your homemade HSM that can serve not many requests, but I don't expect that a single user will generate thousands of keys per hour or something. And yeah, that was it. Thank you.